Hey guys, kind of late on this video, but this is going to be for 4.6 and 4.7. So, let f be a function such that each point xy on the graph of f, the slope is given by the equation stated here. The graph of f passes through the point 1, 2. It is concave down, so that's important to note right there. On the interval from 1 to 1.5, let k be an approximation for f of 12, found by using locally linear approximation at f. So that means linearization, local linearization of f at x equals 1. Which of the following statements about k is true? So first of all, if we're going to make an estimate using k, which is based off of a tangent line on a curve that is concave down. If we take any sort of tangent line here, the tangent line is going to be an overestimate, so we know it's going to be an overestimate right there. So whether or not it's 2.6 and 5.6, well, let's give that a go. So we know that the slope right here is given to us, and we have a point. So if I plug in that point, the slope is going to be equal to dy dx, and that's going to be equal to 2 squared minus 1, which is going to be equal to 3. So my tangent line is y minus 2 is equal to 3 times by x minus 1. And then I'm going to plug in, no, not 1, 2, 1, I'm going to plug in 1.2 right here, which would make that 1.2. So y minus 2 is going to be equal to 3 times by 0.2. And then I get y is equal to 3 times by 0.2 plus 2. And then that's obviously going to be greater than 2. So it's got to be 5.6 right there. So it's got to be A. Okay. Let f be a function. So same type of question. And we have a differential function. And we are going to plug in the point 1, 2. We're going to get a differential. We're going to get the slope. So m is going to be equal to 1/2 times by 1 minus 1/4 times by negative 2. So that's going to be 1/2 plus, that's supposed to be squared. So that's going to be squared. So that's going to end up being minus 1. 1 second. So 1/2, that's squared, because that's going to become positive 4, and negative 1/4 times by positive 4 will be minus 1. So it's going to be equal to negative 1/2. Okay. So y plus 2, using this point right here, is going to be equal to negative 1/2. And then we're going to have x minus 1. So y is going to be equal to negative 1/2. If I plug in 1.3 right here, that's going to end up being 0.3. And then minus 2. So if we have, I'm not sure, that's going to be negative 1/2 minus 2. So y is going to be equal to negative 1/2 times by 1, or 3 over 10, 3/10 minus 2. That's going to be equal to negative 3/20 minus 2, sorry. So 3/20 is definitely going to be less than 50%. So it's got to be one of these two right here. I'm assuming it's going to be negative 2.15. And since the function is going to be concave up, a tangent line is going to be an underestimate. So I think it's got to be C, right? Hold up. If you guys are watching this video, you guys are probably thinking, what the heck? How did I get 5.6 right there? Because I just looked and saw that. That's 2 plus that. That's got to be C right here. Yeah, that's positive 2 plus something. Why did I say 5.6? What in the world was I thinking right there? I don't know. Okay, but negative 2, and that should be, yeah, okay. That checks out, I hope. Okay, for 3, we have a table, and we're making a tangent line. So, y minus 12 is going to be equal to x equals 4. G prime is 2.2. So 2.2 times by x minus 4. Okay, and we're plugging in 4.2. So y is equal to 2.2. Plug in 4.2, we're going to get 0.2. And then plus 12. So we have 12. All of these are 12. 2.2 times by 0.2. I can't see that in my head too clearly. That's 2.2. 2.2 is 2 1/5, right? That's 2 1/5. So that's 11. Is that going to be, is that 11 over 5? Right? 5, 5, 4. And then times by 1 over 5 plus 12. So that's 11 over 25 plus 12. 11 over 25. I still don't even know that off the top of my head. Let me just pull out the old calculator. So 11 divided by 25 is 0.44. So this becomes 12.44. That's going to be A. All right, same type of question right here. We're going to say y minus 17 is going to be equal to negative 1.2 times by x minus 3. And we're plugging in 3.2. So y is going to be equal to negative 1.2 times by 0.2 plus 17. I'm just going to use my calculator now. So negative 1.2 times by 0.2 is negative, so this is negative 0.24 plus 17. And so that's going to be, 7.6, so A. Man, they're really bad at this stuff right here. Am I right? Same type of question. It's going to be same old thing. I hope that's not going to be the case for the rest of this. But, all right, so let g be a differentiable function such that g of 3 is equal to 2. So y minus 2 is going to be equal to g prime of 3 is negative 3/4. And we're going to have x minus 3. And the graph of g is concave down. So that means concave down, which means that it's going to be an overestimate on the interval from 2 to 4. Which of the following is true about the approximation of 2.6? So y minus 2 is equal to negative 3/4. If I plug in 2.6, I'm going to get negative 0.4 here. Okay. So negative 0.75 times by negative 0.4. And then if I add 2 to that, I get 2.3. So should be C right there. Okay. And just like that, we have another problem. So y minus 7 is going to be equal to 1/5 times by x minus 4. Based off of the information given here, the graph of f is concave up. And so if it's concave up, we're going to have tangent lines that are going to be an underestimate. Okay. On the interval from 3 to 5, which of the following is true about the approximation at 3.5? So y minus 7 is equal to 1/5 times by negative 0.5. So we have 0.2 times by negative 0.5, and we add 7, we get 6.9, and so it should be B. Okay, we finally get some different answers there. Okay, on to 4.7. So something that we didn't really talk about too much in class, because I kind of forgot about it, but limits regarding infinity. Remember that 0 over 0 is an indeterminate form, and so is infinity over infinity, also indeterminate form. Now, evaluating limits at infinity, so we have this function given here. Remember that to show, we have to show indeterminate form, because we're trying to find the value of the limit as x approaches infinity of f divided by g. So if I show the limit as x approaches infinity of 3x plus 2 over e to the 3x. So notice that here I decided to put e to the 3x in the denominator for the sake of evaluating this limit right here, because if I evaluate the limit as x approaches infinity here of this expression, it becomes 0. Because if this expression, if x approaches infinity in this expression, then, I mean, this just keeps getting larger and larger. It becomes infinity as x approaches infinity. Now, if the numerator remains constant, though, and the denominator keeps getting larger and larger, then this expression is going to be equal to 0 at infinity. But this expression here is going to approach infinity. So the entire expression is going to approach infinity. So it's going to be equal to infinity. And then as for the denominator, so the limit as x approaches infinity for the denominator, that's already given to us. And so we get an indeterminate form, which means that we can apply L'Hopital's rule. So the limit as x approaches infinity, we're going to take the derivative of the top. So that's going to be 3 plus 2 e to the negative 3x times by negative 3. All over, and they tell us that g prime of x is 4 plus 1 over x. So if I apply the limit at infinity, the same thing kind of happens for this term right here. Again, this right here is going to be 0 as it approaches infinity for the same reason as up here. So this is going to approach 0, but this time, this is going to stay constant. So it's going to be 3 on the numerator. And then on the denominator for this expression, if we apply the limit separately of 4 and 1 over x, the limit as x approaches infinity of this is going to be 0, because as x approaches infinity, 1 over a number that keeps getting large is going to be 0. So it's just going to be 4. And 3/4 will be the answer of that limit. Okay. Let f be the function defined here. Let g be a differentiable function with derivative given by g prime, and it is known that the limit as x approaches infinity of g of x is equal to infinity. Find the value of the limit as x approaches infinity of f divided by g. Okay, so we'll have to prove that the limit as x approaches infinity of f of x is going to be infinity to use L'Hopital's rule. But again, this right here is going to approach 0, and as x approaches infinity of 2x, that's going to be infinity. So it's going to be infinity. Now we can apply L'Hopital's rule. The limit as x approaches infinity of the derivative of f of x, so f prime, is going to be 2 plus 3e to the negative 5x times by negative 5, all over 1 over x plus 4 cosine of 5 over x. And let's apply this limit here. The limit as x approaches infinity of this expression is going to be 0, but I'm going to be left with 2 on the numerator. Okay, all over the limit as x approaches infinity of this expression right here is going to be 0, and it's going to be 0 for here. So this will be 0, and this will be 0, so it's going to be equal to 4 cosine of 0, and cosine of 0 is 1, so it's going to be 2/4 or 1/2. Okay, And then we're just going to be evaluating limits as t approaches 0. Now, because this is multiplication, as long as I can just see that it's going to be equal to 0 over 0, then I'm just going to go, because I don't have to show that on a multiple choice. But so I know sine of 0 is 0, and if I plug in 0 here, I'm going to get e to the 0, which is 1. I'm going to get 2 minus 1, which is 1, and the natural log of 1 is 0. So I get 0 over 0, so I'm going to use L'Hopital's rule. So I don't have to show it, but I still need to make sure that I do get an indeterminate form, or else I'm going to get this limit wrong. So the limit as t approaches 0 of cosine of t over 2e to the t over 2e to the t minus 1. So I took the derivative of the natural log, which is 1 over 2e to the t minus 1, times by the derivative of the inside, and the derivative of the inside is 2e to the t. Okay, and then if I plug in 0, I'm going to get cosine of 0 over 2e to the 0 over 2e to the 0 minus 1. Cosine of 0 is 1 over 2 over 1. That's going to be 1/2. Okay. And then kind of just again, if I plug in 1/2 into cosine, cosine of 1/2 is 0. So the numerator becomes 0. If I plug in 1/2 here, I'm going to get pi minus pi, which will be 0. Okay. So the limit as x approaches pi halves of negative 3 sine of x over 2 minus 0 over just over 2, right? And then if I plug in pi halves, I get negative 3 times by 1 over 2, so negative 3 halves. So the limit as x approaches 0 of sine of 0 is going to be 0. If I plug in 0 here, that's going to be 6. If I plug in 0 here, that's going to be 2. 6 minus 2 is 4. 4 minus 4 is 0. So I get 0 over 0. And then we'll apply the limit as x approaches 0 of the derivative. So the derivative of this term right here is going to be 24e to the 4x. And then minus 6e to the 3x. And then that's going to be 0. And then this will be 2 cosine of 2x. I plug in 0. So I get 24e to the 0 minus 6e to the 0 over 2 cosine of 0. And then I'm going to get 24 minus 6 over 2. 24 minus 6 is going to be, is that 18? And then over 2, so it's going to be 9. All right, and the limit as x approaches pi, secant of pi, secant of pi is still going to be 0, right? Yeah, because secant is not the inverse. Secant is the reciprocal to cosine, but in any case, so that means secant and cosine both utilize the x-axis when you evaluate their values, and at pi, yeah, so pi would be over here, and so if I plug in pi here, secant will be negative 1. So this is going to be negative 1, and if that's going to be negative 1, if I plug in pi here, so pi, yeah, that's going to be 0, because pi plus pi times by negative 1, so pi minus pi will be 0. And if I plug in pi here, I get pi squared minus pi squared, which is 0. So let's use L'Hopital's rule. So the limit as x approaches pi of 1 plus pi, and the derivative of secant is secant x tangent x all over 2x, and then the derivative of this right here is going to be 0. Okay, so if I plug in pi, again, that's going to be -1. Oh man, tangent utilizes both the x and the y axis, but let's just go ahead and do this right here. So at pi, so this is the angle pi right here. The angle pi goes this way. X is going to have to be -1. Y is going to have to be 0. And tangent of theta, we'll say tangent of pi, is going to have to be equal to y over x. So it's going to be 0. So this becomes 0 here because tangent of pi is 0. And that means that we just have 1 on the numerator, 1 over 2 pi. And so it's got to be c. Okay. Okay, now 7. I told you guys in class that 7C was going to be a doozy. Okay. So particle P moves along the y-axis so that its position is given by y of t for all times t. A second particle Q moves along the x-axis and its position is given here for all times that t does not equal 2. As time approaches 2, as t approaches 2, so we can say the limit as t approaches 2. What is the limit of the position of the particle Q? Show the work that leads to your answer. So the position of Q is given here. So we're evaluating the limit as t approaches 2 right there. So the limit as t approaches 2 of sine of pi t over 2 minus t. So if I plug in 2, that becomes 0. If I plug in 2 here, I get sine of 2 pi, which also becomes 0. So I can, oh man, this is a free response question. I hate that rule so much. So I will show that the limit as t approaches 2 of sine of pi t, that's going to be equal to sine of 2 pi, which is going to be equal to 0. And then the limit as t approaches 2 of 2 minus t is going to be equal to 2 minus 2, which is going to be equal to 0. So now I can apply L'Hopital's rule. So the limit as t approaches 2, the derivative of the top is going to be pi cosine of pi t all over -1. Okay, and if I plug in 2 right here, I get cosine of 2 pi, and cosine of 2 pi is 1, so I get -pi as my limit. Cosine of 2 pi is 1, yes. Okay, that's the limit there. So for B, show the velocity particle Q is given by, so show that the velocity particle Q is given by this right here. So is this the velocity? So to find velocity of Q, we take the derivative of its position. So let's see if I take well, I know that it is, but I'm going to take the derivative of this and show that it's that. This is just going to require the quotient rule. So here I'm going to... Okay, so using the quotient rule, we're going to use low d high. Derivative of that is going to be pi cosine of pi t. So low d high minus high d low, which would be -1. And then square the bottom, which would be 2 minus t squared. So they don't quite have this exact same thing. What they're doing, it looks like, so you see how the first two terms have cosine of pi t. So what they're doing is they're multiplying this into both of those. So it's going to be equal to 2 pi cosine of pi t, and then minus pi t cosine of pi t plus sine of pi t, because negative times positive, right? And then all over 2 minus t squared, and we get what they got right there. Perfect. Okay. All right, so now C this is a related rate problem. So find the rate of change of the distance between the particles P and Q at t equals 1/2. Show the work that leads to your answer. Okay, so what we are doing for C, we have the particle P, which moves up along the y-axis. We have the particle Q that's going to move along the x-axis. So this is particle P, this is particle Q, and so they are moving in their directions right there, or they're moving along, I guess. But as they move, we're finding the rate of change of the distance between these right here. So what is the rate of change of the distance between them? So it looks like we're going to be using Pythagorean theorem. Okay, and so we need to use, we'll call this y, call this x, we'll call this z. So z squared is going to be equal to y squared plus x squared. And if you haven't noticed, what I like to do first is take the derivative of the function that I need, and then I kind of just try and see what I need after. Okay, so find the rate of change of the distance between particles. Yeah, we're trying to find that at t equals 1/2. Okay, so that's going to be 2z prime equal to 2y prime plus 2x and x prime. And then the 2's don't matter much to me because everything has a 2, which can be divided out. So I obviously need to find z, y, and x, so I need to find what z, y, and x are. So let's start by finding x and y, and I'm going to find those by plugging 1/2 into y and x. So by plugging 1/2 into both functions that I have right here. So if I plug in 1/2 right here, so y of 1/2 is going to be equal to 2 minus 2/3, right? And then that's going to be equal to 6/3 minus 2/3, which is going to be equal to 4/3. So that's going to be y. And if I plug in 1/2 up here, so x of 1/2 is going to be equal to sine of pi halves over 2 minus 1/2, which is going to be 3/2, or 1/2, so, or 1.5, which is 3/2. Sine of pi halves is 1, so 1/3/2, so this is going to be equal to 2/3. Okay, so I'm going to have, I'm just going to write some information right here. So x is going to be equal to 2/3. I know that y is going to be equal to 4/3. And now I need to find z, so I'm going to use the Pythagorean theorem to find z. So z is going to be equal to the square root of 2/3 squared, which is going to be 4/9, plus y squared, which is going to be 16/9. So that's going to be equal to the square root of 29, which is going to be equal to the square root of 20/3. So that's what z is equal to, square root of 20 over 3. Okay, now I'm trying to find z prime. Y prime is going to come from the derivative, so we need to take the derivative of that right there, and the derivative of that is just going to be 4. And so y prime is going to be equal to 4. X prime, this is kind of where the worst part comes in. X prime is going to be, well, we already found x prime. X prime is here. So this is what x prime is, and so you're going to plug in x prime for that right there. You're going to plug in 1/2 for t right here, and you're going to get x prime, and then you're going to have everything that you need for that right there. So I think I've carried a lot right there, and I think you can make it the rest of the way, so we're going to call it there.